Thanks everyone for coming to this talk. It's great to see a room full of ECMA-419 aficionados. The title of this talk is ECMA-419, the ECMAScript Embedded Systems API in J5e, which is a bit of a mouthful. I've decided it's the worst title for a talk ever. Should have called it the future of JS robotics, the future of JS IoT, the future of smart things with JavaScript. But no, I called it ECMA-419, the ECMAScript Embedded Systems API in J5e, because I'm not very good at marketing. I want to let y'all know that I'm not really going to read the slides, except when it's important for context. They'll just be like sidebars for the rest of the talk. My name is Donovan Buck. I'm DTechs at GitHub and Twitter. I'm a contributor to various open source projects, robotics, JavaScript projects, and IoT projects. And I'm an invited expert at ECMA TC53, the committee responsible for ECMA 419. So before I dive into 419, I want to talk about the history of JavaScript on hardware. And it goes back over 10 years. I want to explore a little of that history to help set the stage for ECMA 419. Most of us come to JavaScript via the web or node.js. And it was with node.js that JavaScript on hardware really became a thing. Johnny 5 was built for node.js. A lot of you are probably familiar with Johnny 5. It's a robotics and IoT framework created by Rick Waldron back in 2012. It's been the standard bearer for JavaScript on hardware ever since. It's been used at hundreds of hackathons to teach thousands of people who've never worked with hardware how to do so in a language that they already know. But it's also been used to teach people who've never written a single line of code in any language. It's how I learned to work with hardware. It was a wonderful hello world hardware experience. And because of the great experience I've had, I've become a contributor to Johnny 5 and other JavaScript robotics projects over the years, because I want to help other people have the exact same feeling that I had. This program that you see on screen here is a typical Johnny 5 program. It's the hello world that I was referring to. Where all we're doing to make it happen is requiring a couple classes that we're going to need, a board and a device. We're instantiating that board. When it's ready, when that event fires, we're going to instantiate an LED and tell it to blink. It's hard to imagine that programming hardware could ever be easier than that. So, let's talk about the Johnny 5 architecture, because it did influence ECMA 419 to a point. There's important similarities, but there's one major important difference. So this is the prototypical setup where we have Johnny 5, which is a collection of peripheral classes, the different things that we might want to control, motors, servos, LEDs, etc. And we have Johnny 5 running on a host computer, which is typically, whoever's building something, it's their laptop, which is of course running an operating system in Node. And it's using Fermata to talk over Node serial port to a microcontroller. Over a USB cable, typically. There's software on the microcontroller that listens for commands from the host computer. The software on the microcontroller never changes. All the logic lives on the host computer. It's essentially a remote control, is what it is. People would build, at hackathons, they'd build their sumo bots or their soccer bots or whatever. And there's a question that kept coming up. Do you have a longer USB cable? Because it's a drag to follow your robot around the room trying to control it while you're holding your laptop. But yes, there were ways around that. You could change out a component at the Fermata I/O level or at the node serial port level to change the transport layer that we're using to talk to our hardware. We could switch it out with Wi-Fi or Bluetooth. And the cool thing was that the Surface API for Fermata did not change. So the program that the user had written did not have to change. Johnny 5 did not have to change. We could control hardware differently using the exact same code, save for requiring one different I/O plugin. But still, there were problems. Why does my robot go to sleep, or why does my robot stop when my laptop goes to sleep? Because it's still remote control. So there's another way to solve that problem. You could just put a computer on your robot. We could use a single board computer, like a Raspberry Pi. We move it onto the hardware itself, or move it onto the robot itself. And it's running Node, it's running Linux, it's running everything on board, and it's got GPIO that we can talk to. And we can switch out that Fermata I/O layer with a plugin called Raspberry I/O, which presents the exact same surface layer, the same Surface API as Fermata, but instead of communicating with the hardware over serial, it just uses C bindings to talk to it talk to local hardware over and control the GPIO there. Again, there were no changes required to Johnny 5. There's no changes required to the user program, save to require a different plugin. It all just kept working. But single board computers are expensive, and prices is a problem because everybody wants to build something, right? IoT products require cost-effective embedded systems, and single board computers are not cost-effective. They're great for hobbyists, they're great for prototypes, but they're not great for entrepreneurs. So we came up with another, and to beat a dead horse, we came up with another solution. We switched out the Fermata I/O layer with another what we call I/O plugin. In this case, this Imp I/O is the one I want to talk about. And companies like Electric Imp and Particle had services where they offered hardware and then a cloud service that lets you communicate with that hardware wherever it was in the world. So we just replaced that Fermata I/O layer, and we're able to communicate with hardware in a completely different way. This over HTTP to a turn server, down to users' local Wi-Fi, and control their thermostat, their robot, whatever. So we've gone through 4 different hardware stacks here, which is pretty cool, without changing the Johnny 5 code or the user program significantly at all. The Fermata JS API became a de facto standard for hardware on JavaScript. But sadly, through all of these stacks, you still need a host computer. And of course, people would always ask, can I just run Johnny 5 on the microcontroller? And sadly, no, you cannot. Johnny 5 needs Node. Node needs an operating system. And the microcontrollers that we're talking about are tiny. They may only have 32K of RAM for your code. So it wasn't going to happen. It's impossible. I acknowledge the value of such a thing. I acknowledge the need for such a thing, but it just wasn't going to happen. However, if we were going to try, there's a couple things we're going to need. We're going to need a JavaScript engine that runs on a microcontroller, and we're going to need access to that microcontroller's I/O. So JavaScript engines for microcontrollers are just magnificent accomplishments, and I don't want to poo-poo any of these projects, but they all left me feeling a little uninspired. They were either subsets of the language, or they were built to old versions of the language, old specifications, ES 2015, things like that. So they were kind of meh. We're still going to need standard I/O, because if we're going to take time to build something like Johnny 5 for embedded systems, we can't have every embedded system have a different way to communicate with the hardware. We want to build it once and have it work for a lot of people out there. That was the thing that the I/O plugin ecosystem back in NodeBots provided. We didn't have that. But at JSConf in 2018, Rick Waldron, the inventor of Johnny 5, pulled me aside, and he wanted to show me the XSJS engine from Moddable. He was really excited, and he had a gleam in his eye. I've never actually seen the gleam in someone's eye, but that was a gleam in his eye. He was very, very enthused, and he was showing me this JavaScript engine, and I was like, yeah, okay, thinking of those other projects, I've seen things like that before. What's the catch? Is it transpiling to squirrel? What's left out of language? He's like, no, this is the real deal. It's legit. And it's quite true. There's a lot of things that I used first in XS because they were available there before they were in V8. So it's very much on the cutting edge of the language, and you get to play with all the cool new things even earlier if you're using it. It was beautiful, but still it had a proprietary API for I/O. And I, wanted to build Johnny 5 for embedded systems, but I didn't want to do it and be tied to one platform. So some time passed. Oh, actually, why is that standard API so important? With Johnny 5, I could build something like a GPS class for one device, the Arduino in this case. And without having to do anything else, it would just work on all the devices that Johnny 5 supported. So that was a really nice, and that's the kind of experience that you're going to want to have if you're developing for open source. So some time passed, then I got an email just completely out of the blue telling me about TC53, ECMA, Technical Committee 53. They were forming, and they were tasked with bringing standards to JS for embedded systems. And the first thing that they were going to work on was a standard JavaScript API for direct access to underlying hardware, digital, PWM, all the things that we need in order to control that hardware. So I traveled to the first in-person meeting as an invited guest. I was kind of nervous, kind of terrified, to be honest. But everyone turned out to be really nice. It was a good experience. But in the opening remarks, someone referenced the question that shall not be asked. And so I lack tact, by the way. And I raised my hand and I was like, what's the question that shall not be asked? Why use JavaScript on hardware? It's slower, it consumes more resources. Why would you do it? But I was wondering, if we don't have a good answer to that question, then why are we even here? Why does TC53 exist? We need to answer that question. So I'll admit that those cons are true. It takes more resources, it's a little slower, but there's a lot of good reasons to use JavaScript on hardware. Let's start with the language itself. JavaScript's runtime model is built on an event loop. That event loop executes code, it collects and processes events, it executes subtasks, and it's patient throughout this process. JavaScript is designed to wait for user input, to interact with things in the real world, in this case in the browser, right? This model, this event loop model, is necessary for working with hardware, and it has to be scaffolded in other languages like C. If you've worked with an Arduino, they give you the loop method. That's not part of C, that's something that they've added on to give you that ability to loop through things and check the state of everything, which is still kind of a clumsy way to do things, but at least it gets you rolling. So the second thing I want to talk about is not really part of the language, but it's a pattern in the language, and that's event emitters and listeners. It's my personal favorite thing about working with hardware in JavaScript, where I can just have a listener button on press, light on. It makes it super easy to model those real world interactions with UI, with hardware inputs. This is actually from a talk that's more than 12 years old. This is from JSConf EU 2010. And they were just kind of looking into the future. This was before JavaScript on hardware was really a thing. And they were talking about how JavaScript as a language kind of fit beautifully with real world hardware applications. And in this particular example, I don't find inspiring where they're chaining methods on a single object, where they're telling the lights to go to 75% and then dim after 120 seconds. But it did inspire one person, Chris Williams. He wrote this in a blog post in 2012. Oops, sorry. By modeling real-world objects and actions as chainable, evented processes felt almost natural. And he was inspired enough and had enough need to go out and create Node Serial Port. Node Serial Port enabled Fermata. And Fermata enabled Johnny 5. All these things exist because JavaScript is a great language for hardware. So back to the language. Asynchronous operations. There's multiple ways to handle asynchronous code built into JavaScript, and you're free to choose the one that works best for you. And there's more than just language when it comes to JavaScript. Love it or hate it, JavaScript is eating the world. It's the web's lingua franca. Most web APIs that we access, and if you're building an IoT device or a smart thing, there's a good chance you're going to be accessing web APIs. They use JSON in the request bodies or the response bodies in order to communicate. And while there are JSON parsers available for most languages now, JSON is JavaScript, right? It just works in JavaScript. So it's not going to be better or faster than what we have available in JavaScript for us. And there's some exciting things happening. If you were in this room for the talk before mine, where James Snell was talking about the Web Interoperable Runtimes Community Group, which is another mouthful of words, where they're looking to standardize those APIs that are not part of JavaScript per se, but are common to multiple hosts, whether they be cloud providers or Node or Dino or the browser. So there's some exciting things on the horizon. And then there's community. If you need to write something, there's a really good chance somebody's already written it in JavaScript and it's on NPM. There's an abundance of references, there's an abundance of developers. This is an interesting stat. This is from a survey earlier this year. There's 3,800 embedded JavaScript developers, 3,800 embedded developers in the United States right now. But there's over 240,000 web developers. So if you're starting a business, if you're an entrepreneur, you have an idea for a product, there's a much larger universe of JavaScript developers at your disposal to come in and get you going, get that prototype, get your funding. So it makes a lot of sense to look to alternative languages. That's my case for JavaScript. Other people will talk about its internationalization tools, its support for Unicode and more. Again, there's just a huge universe, an ecosystem of work out there that you can build upon. So, back to TC53 and ECMA-419. TC53 created a standard API for access to underlying hardware, and that standard is ECMA-419. I did ask the Secretary General if it could be ECMA-420, and he said no. It went through and it standardized all those things, and I'm going to tell you right now, as a node developer, I was a little frustrated with it, and here's why. I wanted those things that I talked about in the language, the event emitters, where you close the circuit, the light turns on, you open the circuit, the light turns off. There's no schedule, it happens many times whenever the user wants to do it. And the new ways of handling asynchronous code, I think, are really wonderful, and they're really nice to have when you're programming in JavaScript. But we've done everything with callbacks in ECMA-419. Why is that? And then I was reminded that the devices that we're building for are humble little microcontrollers. And while XS, for example, has all those modern features of the language, those other engines that we showed earlier do not. And that needed to be a guiding principle for TC53. So let's talk about guiding principles real quick. This slide has language from the Extensible Web Manifesto, but it's been edited so that it's not web specific, but it still captures the intent. We're going to focus on adding new low-level capabilities that are secure and efficient in order to allow library authors to iterate on libraries that provide developer-friendly high-level APIs, and free up the standards process to focus on features that can only be added at the platform level. So this focus guided the work of TC53, as did the Waldron principle, which states that everything in hardware can be modeled as a series of read and writes, which is simple but true. And the natural result of those two principles was ECMA-419. So let's talk about the parts of 419. There's I/O classes, which are classes for all the connections to hardware peripherals that we might need. Digital, analog input, PWM, serial, et cetera, all the ways that we communicate with different devices. They have a constructor, pin specifier, and a port specifier. All of them do. They all have read and write methods, depending on whether they're input or output, of course. And they all have a format property, so we know what kind of data they're serving up to us. And then they all have 3 callbacks: on readable, on writable, and on error. That's it. It's that simple. So a very consistent interface for those I/Os. We also have providers. A provider is a collection of one or more I/O classes. Generally speaking, it represents a device that is connected to the host hardware or is the host hardware, but it could be connected via I2C or a 6-foot USB cable or located halfway around the world and you're talking to it over the web. But ECMA-419, or the program that the user writes, does not care. The difference is in the providers. So peripheral classes, those are for accessing the different kinds of hardware that we're going to talk to. Going back, Johnny 5 is a collection of peripheral classes, right? We just wrote those on top of Fermata IO and Node Serial Port. So ECMA-419 also has a collection of peripheral classes to guide other developers who are developing new peripheral classes. Those are peripheral classes in general, I think, are not going to come from one place. They're not going to come from 419. They're going to come from open source developers who are following the standard that's set forth by ECMA-419. So sensor classes are a subset of peripheral classes. They're all the things that we use to gather input from the real world around us: thermometers, gyroscopes, whatever. And of course, display classes, which are one of the things that set JavaScript apart, and its ability to create those beautiful user interfaces on a microcontroller, on a small device with a small touch screen or a small display screen. So let's look at how a program would have been written with Fermata IO without Johnny 5 available. Here we have this board first philosophy. Where we're instantiating a board, and Johnny 5 is aware of all the things that the board has and can do. So it's managing the hardware. So once we instantiate a board and we get a ready event back, we're going to choose a pin and we're going to set its output, or we're going to set its mode to be output, and then we're going to toggle its state every 500 milliseconds. So with ECMA-419, it's similar but different. We are not worried about the board. In this case, we are using the host's built-in GPIO. So we're not worried about the board at all. That's managed by the host. All we have to do is request from devices.io, which is built in on the host. All we have to do is request the digital class, and then we can instantiate a digital pin on whatever pin we choose, here 14, and then we're toggling the state every 500 milliseconds. And I struggled with this slide a little bit, because here's where I was going to talk about how ECMA-419 is different than the IO plugin ecosystem. But the important part is not how they are different, the important part is how they're the same. They present a consistent IO API that works across multiple devices and architectures, so we can write code once and have it work on a variety of platforms. So I got everything I needed in 419, but I didn't get some of the stuff I wanted. I had mentioned I was frustrated. Like, where's events? Where's async stuff? Why aren't we doing this? We've got everything with callbacks. But I remembered this part of that modified extensible web manifesto, where we're going to allow library authors to iterate on libraries to provide developer-friendly, high-level APIs. And I thought, I'm a library author, and I want some developer-friendly, high-level APIs, so let's make this thing. So we have J5e for embedded systems now, built upon ECMA-419. We were able to get port classes straight from J5e, but we were able to strip out a lot of code. So in the case of LED, we don't care if the pins are built in or located halfway around the world or attached to your computer with a USB cable. As long as we have a provider that follows ECMA-419, it will just work. It has all the same methods, all the same properties as J5e, but we were able to delete a lot of special code for things like expanders and special kinds of boards that we had to manage in J5e, because the ECMA-419 model takes that away. But we were able to keep everything that makes it special. So you saw this program earlier, where we're requiring our class, instantiating a board. When the board is ready, we instantiate an LED and tell it to blink. That's the hello hardware world that gets people really excited at a hackathon. With J5e, we can just do this. We can import the class from J5e, instantiate an LED, and tell it to blink. We're using subpath exports with either a manifest file or package.json, depending on the platform, to get just the parts that we need, so it's very small. There are no dependencies to J5e. It's self-contained, so you don't have to worry about bloat or importing a bunch of different modules, because again, we're targeting tiny little devices, so we want to keep things as small as possible. We are using top-level await here. When we are instantiating our LED, we can get away with that because we're using an asynchronous immediately invoked function expression on the constructor that returns. It's possible to not do that. You can wrap this in an async function and actually get a little better performance out of your program. But if you're teaching someone JavaScript, this is a really nice way to do it because there's a minimal amount of computer vomit. So really great way to teach people to program. There's 3 lines in this program, and there are 3 clear, unambiguous verbs. We're importing the LED class, we're awaiting a new LED, and then we're telling it to blink. So I think that's the new standard for easy hardware programming. This is it in action. I didn't bring hardware. I have hardware with me if anyone wants to stop me and check out some demos. But the program is installed on the microcontroller. Right? You don't need that host computer anymore. All I'm doing here is applying power. It just fires up and starts running. And that's a really good feeling. It occurs to me now that it also makes hardware demos a lot less intimidating. So we've got in J5e already a group of classes that are available to use. LED is the perfect prototypical one because it uses digital pins and PWM output. Servo uses a special flavor of PWM. We've got that working. Switch and button use digital input, so we're kind of testing all these different I/O classes with J5e. Animation and easing are fun because they're kind of computationally expensive. We have all the same kind of easing functions that you might find in something like jQuery UI when you were animating things across the screen. We have a generic sensor, which uses analog input. Basically anything that attaches to an analog to digital converter you can use with J5e. So flex sensors, photoresistors, thermometers, all that kind of stuff is really nice. We have GPS class in there that uses serial to communicate both ways with the device. And coming around the corner, we have an I2C-based device, an expander that allows us to control multiple PWM pins. So I'm pretty excited about that. If you want to check it out, you can at j5e.dev. All you need is an ESP8266, which is a few bucks at AliExpress, or an ESP32 if you want more room to play. Also, Moddable has some really beautiful ESP32-based devices with built-in displays. Pretty awesome and worth checking out. But there's a wide variety of devices that fall between those two that you can get and experiment with. And I'm happy to answer any questions. I got about 5 minutes left. Yes, yes.
For the simplest case, the J5e and ESP, you have to install a JavaScript separately, or you want to that all together?
So the way it works right now is you write your program in using J5e, and there is a build step that takes everything, bundles it, and sends it to the ESP32 or ESP8266. So it's not there waiting for you. It all gets bundled up every time you rewrite, every time you make a change to your program.
You don't have to worry about where the JavaScript
Right. Yeah. And yes.
How many hardware hacks have you made yourself?
How many hardware hacks?
Yeah, just doing a big pants. What's your house like? I'm sure it's
Actually, not that much. I spent a lot of time building a hexapod that ran using JavaScript several years ago. That would be the thing that I would point to and say, you know, wow, look what I made. But a lot of little things just basically to test things out. I gotta be honest, I get more excited about making things and seeing other people build upon those things. That's a really cool feeling to walk into a room and see people running code that you know, that's built on top of something you made. So I spend more time doing that than actually building my own things. That said, we've done a few. We did a telepresence robot at a robotics club there in Houston that ran on Johnny 5. It was 6 feet tall with an iPad, and you could walk around the room. It was awful. It looked horrible, but it worked really well. It was a lot of fun. Any other questions? Yeah, Brian.
So this might be putting the cart before the horse, but have you had any discussions internally about updating support into, say, actual browsers themselves that might be running on, say, a Raspberry Pi, where they would have access to these peripherals?
So I don't have personal experience with, was it Web USB? That would enable a browser to talk. Actually, I don't know that you need USB necessarily. But there's nothing stopping us from creating ECMA-419 conformant APIs for all different stacks. You know, it occurred to me that we could write an ECMA-419 conformant Raspberry IO stack. You know, that kind of goes in where Raspberry IO is and communicates with PyGPIO. So I think, you know, if we standardize on ECMA-419, then it gives us a lot of options and the ability to build a community around a standard. Instead of, right now, you know, when you look at microcontrollers and hardware, especially going back a year or two or more, it's the Wild West. It's where browsers were 20 years ago, where everyone's kind of doing their own thing. So that's why ECMA-419 is really important for the future of JavaScript on hardware, because it brings everyone and rowing in the same direction. Yeah?
So I have a ESP6,
Mm-hmm.
so far, the only code I deployed to it is through Arduino and C code.
Mm-hmm.
I'm just wondering, we're talking about doing all this with JavaScript.
Mm-hmm.
Like, how, like, are you doing this through Visual Studio Code or just Arduino? Like, what's the process to like get the JavaScript environment for you?
So Moddable has an SDK that has bundlers and compilers. They've kind of gathered all the things together that you need. So that you can just go through and run a program that they have, an MC config, and it in turn calls the build tools and deploys it to the ESP32 or 8266. And that's what this is built upon right now, because it's the only 419 conformant system out there, or platform out there. But it handles all of that for you. It's the Moddable SDK. Moddable SDK will help you get there, yeah. Or if you go to j5e.dev and go to the Getting Started page, it'll point you there as well.
Okay. Thank you.
Sure. Alex, time?
Online question.
Oh, yeah.
What IDE would you recommend for best integration/use?
Whichever one you like the best. It really doesn't matter. It's a text editor. I use VS Code, but work with what you like. It really doesn't matter. Yeah.
How would you test?
How would I test what?
The code that you're writing?
So what I did for J5e, J5e runs in Node as well. There's just no 419 conformant IOs that I can talk to yet, or providers that I can talk to yet. But I'm doing all my testing in Node. That has burnt me on one occasion just where the JavaScript parser is different, or the JavaScript engine is a little different for resource constraint reasons. But for the most part, it works really well.
Do you just like mock your LED?
Well, I mock the IOs. Yeah. So ideally, there would be something that actually tests on hardware. I haven't got there yet.
So if you're on, say, like in your WSL and you ask for like a 1014, that's where it's mocked, I guess, or would it?
Yeah, exactly. There's a mock IO that follows, that kind of loosely follows the ECMA-419 specification, so that it appears to be operating. We're going to add some classes on top of it so that we can force a state change.
What would happen if it doesn't have, you know, the device doesn't have it, if you're saying like you're on the
So it's going to depend on the host and how the host chooses to handle that. I think, you know, I'm not sure off the top of my head. I think it's going to throw an error. You know, working with the Moddable SPK has been really nice because it has a very nice, it's called excess bug, so a debug console that shows you the errors returned from the microcontroller as long as you're running in debug mode. And that's really slick, and that makes it easy to solve those kinds of problems. Whereas on the Arduino, you know, it fires off into space and you're like, what happened? I don't know what happened. So it's really nice. All right, cool. Well, I guess we went a little over, but thank you all for the questions. All right, thanks everyone.